Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on what I have termed DES toy. We're using a toy version of DES. DES is a very complicated algorithm that I think was made in the 70s. It is used for data encryption. It does heaps of different things to plain text to produce some ciphertext. It's just not secure today with modern computers. But the algorithm itself is very complicated. It's beyond the scope of this course and it's far too complicated to do by hand. So what I've done is I've just come up with my own algorithm here that sort of gives some indication as to what DES does. So let's use this to encrypt the message AAD, which stands for attack at dawn. So the first step in this algorithm is to turn the plain text into a bit string. The bit string from the ASCII table. You can look that up on Google or look at the notes. So capital A, remember capital letters and lowercase letters have different strings to represent them, but capital A is represented decimal number 65. So in binary, I'm going to use an 8-bit string. So we always put a 0 at the start, so it's 8 bits. It is 0, 1, 0, 0, 0, 0, 0, 1, and the next capital A will be the same. So capital D from the table is decimal number 68. So in binary, we're going to start with a 0 so that it's an 8-bit string, and then it's 1, 0, 0, 0, 1, 0, 0. So this is our plain text and we are going to operate on these numbers here. The second step in the algorithm is we divide it into two halves. I've called them L0 for left and R0 for right. So this has 3 times 8, 24 bits. So we're going to divide it in half here. So this here will be the left half, L0, and then of course this will be the right half. So step 2 is done. So I'm going to choose two keys, K1 and key 2. I'm going to make them 12 bits long, and then I'm going to use the first key to XOR with the right half. The second key I'll XOR with the left half. Remember, this operation here is XOR. So let's choose the 12-bit keys. I'm just going to choose them at random. So here I have my K1 and K2. Doesn't really matter which is K1 and K2. So by having these keys 12 bits, they're not the same length as each character. By dividing it in half and using different keys, I will have a situation where I don't have the same letter always being mapped to the same letter. Okay, let's XOR these. So there's a lot of operations to do because they're 12 bits each, but it's really easy to do. Remember, XOR is just addition modulo 2. So 0 and 0 gives 0, 1 and 1 gives 0, because 1 plus 1 is equivalent to 0 mod 2. 0 and 1 always gives 1, 0 and 0, and so on. So once you get the hang of it, you can do these quickly. So once again, we have a 1 plus 1 modulo 2 is equal to 0. All right, now we're going to go on to the next half of the data, 0 and 1, 0 and 1, and so on. So this here is just how you would write in a code that we're going to now switch these two halves. This will become the left half, this will become the right half. So now what we're going to do is expand the data, which is sometimes done in these algorithms. So we're going to take the base 10 reduction modulo 16. So we're going to turn this into base 10 and reduce it modulo 16. So you can use an online calculator to help you if you like. So we have 1, 2, 4, this is in the 8s column, then 16, 32, 64, 128, 256. Next one is 512, 1024, and 2048. So that in base 10 is the number 3464. We're going to do the same with this string here, write it in base 10. So this is the number 567. We are going to reduce each of these modulo 16. So it turns out we've got 8 and 3 respectively. So what we want to do is add 8 and 3 onto the end. We're going to add them in binary, but what we're going to do is we're going to use 4 bits, because if I use 4 bits in this half and 4 bits in that half, I've added 8 bits. It's like an extra letter being added, and that makes it a little harder for someone to decrypt if they've intercepted the message. So I'm going to write 8 in 4 bits. So taking my new left half, 8 in 4 bits is 0, 1, 0, 0. I added that extra 0 at the start, so I'm adding on 4 bits. And I'm going to do the same here. I'm going to take this string here and add 3, but I want to use 4 bits. So that will be 0, 0, 1, 1. So my message, which started off with 24 bits, is now 32 bits. That sort of scrambling makes it a bit more secure. But this is really hard to read. So what we might do is we might turn this into hex. So how are we going to do this? We don't want to write it as just one number in hex. What we're going to do is we're going to take blocks of 8 bits and turn each of them into hex. So I don't mind if you use an online calculator to help you with this. So this is the decimal number 216. So in hex, it would be written as D8. It is 13 times 16 plus 8. This is the number 132, which is 8 times 16 plus 4. Then we have 54, which is 3 times 16 plus 6. And then the final is 51, which is 3, 3. This would be the final message displayed in hex. You can see that it is absolutely nothing like the original, and it kind of makes it appear like we started with 3 characters and ended up with 4. So that just makes it hard to decipher. So make sure if you're writing it in hex, you always use the same number of digits for each block, or that means that decrypting will become much harder, almost impossible even if you have the key. It'll cause some confusion because there'll be some ambiguity there. So remember that this algorithm that I've made up, it wouldn't be secure. Computers would be able to break this easily. It's just to give you an indication of some of the things that DES does. DES was very popular. It is a symmetric key algorithm, so same key for encrypting and decrypting. But it's very complicated, and I hope this video has given you some indication of what goes on. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.